Today we'll discuss linear programming, which is the application of systems of linear inequalities. Start by looking at the problem in front of us. We know we've got three lines that we have to go ahead and graph. They're mostly in slope-intercept form. We can either use that or the intercepts like we've done before. This is set up simply in slope-intercept, so I'll graph. So this guy I'll use intercepts for, so I have 0, 6 and 3, 0, 0, 6, 3, 0 puts me right on here. Connect the dots. And finally, we have 2, a vertical line, and 6 on a vertical line, and we're shading between the two. So that gives us this region here for my triple shaded region. I need to find all my corner points. So in this case I have 4, but they're all pretty easy to find because I know the x values on them. So in this case we have x equaling 6 here, 6 here, 2 here, and 2 here. You just have to plug back into the correct equations to find the y values. Let's start with x equals 2 on the blue line. This is the equation of the blue line. If x equals 2, y is equal to 8. And then let's go down to the green line. Here's the green line. If x equals 2, y is equal to 2. Let's move over and plug in 6 to the blue line. If x equals 6, y equals 12. And then let's go to the green line. If x is equal to 6, y is equal to negative 6. So now I have four corner points or vertices of this feasible region. And the problem when I do linear programming, you're usually asked to maximize or minimize a quantity. They will give that quantity to us. And the equation they're asking us to maximize is negative x plus 3y. And what I do is I take all these vertice points, so 2, 8, 2, 2, 6, negative 6, and 6, 12, and I plug these points into my maximizing equation, see what I end up with. Plugging in 2, 8, 24 minus 2 is 22. Plugging in 2, 2, that's 4. Negative 6, or 6 and negative 6 give me negative 24. And 12 and 6 give me 30. So this last point gives me the greatest value and thus maximizes the equation. The maximum value is 30 at the point 6 and 12. So pretty straightforward. I've already given the equations. Now when we really talk linear programming, we talk about getting word problems and then finding the equations for those, graphing them, and solving them. So in all these types of problems, you'll be given what we call an objective function. And what an objective function is it tells you what you're maximizing and minimizing. It's always good to find that first. So if you read through this problem, you'll notice that down here it talks about how many planes of each type are needed to maximize the cargo space. There's your objective function. We're trying to maximize the cargo space. So we max cargo space. I'm going to look for information regarding cargo space. So I read through the problem, and this talks about cubic feet of cargo space, as does this. And it says I have large planes carrying 30,000 cubic feet, small planes 20,000 cubic feet. So let's go, large is X, so 30,000 X plus 20,000 Y is equal to my max. Now I know the X values are my large planes, the Y values are my small planes. Next, what they're going to do is they're going to talk about some constraints. And constraints are basically limitations to what you can use in the problem. So I look in this first sentence and it says I have a total of 44 planes. That's a constraint because I can't go over 44. So I'll write that down. And then I read through the problem some more. And it says I have a total of 128 crew. So it appears that those are my only constraints. The next thing I need to do is I need to write an inequality describing those constraints. So when I say I have 44 planes, I can't go over that, so it must be less than or equal to, and I can't go over 128 crew. That's also less than or equal to. Now, it states with the crew that large planes get 4-person crews and small planes 2-person crews. So I can say 4L plus, 4X plus 2Y is less than or equal to 28. And then the total number of planes, well, that's large planes X and small planes Y. Next, I'll go ahead and label my axes and graph. I'll take and call each of these, let's go, we'll go 10, 20, 30, 40, 50, 60. Likewise here, 10, 20, 30, 40, 50, 60. And then I'll go ahead and use intercepts to graph these functions. So in the first one, 44 and 0, 0, 44. For the second, I have 128 divided by 4, so when x is equal to, or when y is equal to 0, I have 32, and then set x equal to 0, and I'll have y is equal to 64. So go ahead and graph those. Where's 44? Right around here, and right around here. Go ahead and connect those two dots. And then I need to graph 32 and 0. 32 puts me around here. 64 puts me about here. Connect those two. It's close. So here's the intersection point. Shading below on both. I have my corner points of my region. So those are 0, 0. I have 32, 0. I have 0, 44. And then I'd have to actually find the intersection of those two. So I can do that once again by multiplying that top equation by -2. I get negative 2x minus 2y equals negative 88. And I have 4x plus 2y equal to 128. Add those up, you get 2x is equal to 40, x equals 20, which means y would equal 24. So this is the point 20, 24. And then I'm going to use each of these points and my maximizing equation to figure out which gets me the maximum cargo space needed. So once again, I have 30,000 x plus 20,000 y. Let's see which gets me the max. This gets me 0. It's not helping much. This gets me 96 and a bunch of zeros. This gets me 88 and 5 zeros. And this gets me 60 and 48, which is 108 and 5 zeros. So clearly, this 10,800,000 is my maximum cargo space, and I get that with 24 or 20 large planes, 24 small planes. I'm going to do a couple more. Once again, I'll let you read through that problem, look for some information, and then we'll talk about it. You'll see that in this case, we're trying to determine minimum cost. So I look for the cost in the problem. I have 70 cents, 30 cents. So we say 0.7x plus 0.3y equals a min. And in this case, we're talking about soybean protein powder and milk protein powder. So x will be my S value. So let's write that in. And the y will be my milk value. Let's go ahead and find some constraints. It says the breakfast must contain 12 grams of protein, 8 grams of carbs. Read through, see if we can find any more. Doesn't look like it. And it's got to contain at least that, so I've got to be greater than or equal to on both. So now let's write an equation for protein. Here's some protein, and here's some protein. So this says the protein powder made from soybeans has 5 grams of protein. Protein in the milk solid has 2 grams. Then I read through and look for milk. Or I'm sorry, I read through and I look for the carbohydrates. Here's some carbohydrate information. And here's some carbohydrates. So I have 3x plus 4y greater than or equal to 8. I can graph all this once again. Again, I'm going to use intercepts. So when I set x equal to 0, y is equal to 6. And when I set y equal to 0, x equals to 12/5, which is 2.4, right around there. So let's go ahead and do intercepts again. When x is equal to 0, y is equal to 2. And when y is equal to 0, x is equal to 8/3, which is 2 2/3, or 2.6 repeating. All right. We'll go ahead and graph these once again. 6, 0. Let's go by 2. So this is 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6. So if I graph 6, 0, or 0, 6, I'm sorry, puts me here. 2.4 puts me right around here. I'm going to connect those two dots. Like so. 0, 2 going to put me here. And 2.6 is right around here. Connect those dots. So. And now I'll take and look at the shading here. 0, 0 is going to not be a solution for each, so I shade above, which means my shaded region is over here. I have corner points of 0, 6, and this appears to be 2.6 repeating and 0. I need to find this intersection point over here. Once again, I will solve this system, and multiplying the bottom or the top equation by -2 should do that for me. I'll go over here and do that. So I get negative 10x minus 4y equals negative 24. Then I have 3x plus 4y is equal to 8. Add those up. Get negative 16 is equal to negative 7. So x equals 16 over 7. Then I'd have to find y. Turns out y is equal to 8 over 21. I have to plug each of these into my minimizing equation. So let's go ahead and do that. In the first equation, after plugging that in, I get 1.8. Second equation, I end up with 1.86 repeating. And in the third equation, I end up with 1.71. So here's my minimum value, 1.71 or $1.71, and I'm supposed to use 16/7 of the soy and 8/21 of the milk. So this last problem will be a little more difficult because we introduce one more constraint to the problem. Reading through, we find out we're trying to maximize the number of people processed. So let's look for information regarding people. Here I see people 300 type for unit A and process 500 people for unit B. So let's go ahead and write 300 x plus 500 y equals a max. And again, x is going to be a and y is going to be B. So then we'll find our constraints. Reading through, it seems here's one right here, $75,000. That's a maximum budget. And then 18 people. And then reading through a little bit more. Oh, right here we have to buy at least 4 units of B. So 4, and it could be more than that, of B, which is Y. So now I look for information regarding how much these cost, and it appears that A is $5,000 each, and B is $7,500 each. And then to run A, I need 1 guard, and to run B, I need 2 guards. So there are my equations. Let's go ahead and find my intercepts. That's 15, 0, and 0, 10, followed by 18, 0, and 0, 9. And let's label these by ones, I guess. So it's 5, 10, 15, 20, and 5, 10, 15, 20. Going through, here's 15, 0, and 0, 10. Going to connect those 2 dots. I'll again go to 18, 0, 0, 9. Connect those 2 dots. Followed by y is greater than 4. Draw a line across here. These 2 are going to shade below, and this one will shade above, so it appears that my solution region is in this area here, which means I have to find an intersection point here, and it appears the green is above, so this guy right here. So I'll need that point where y is equal to 4, and it's intersecting the green line, which has, this is my equation, and if I'd drawn that accurately, I'd end up with 9. Now I need to find the intersection of these 2 equations, because that's the blue and the green, and this is going to get me 6 and 6. So now I look at these intersection points here. Clearly this is 0, 4, and this is 0, 9. So I'm going to use these 4 points to check my maximizing equation. 0, 9, 0, 4, 6, 6, and 9, 4. Plugging into my maximizing equation down here, we end up with 4,500 for the first, 2,000 for the second, 4,800 for the third, and 4,700 for the fourth. So having 6 of each machine is going to get the job done. That's pretty much all we've got. A little bit involved, but I think you'll get through it. Do your lesson summary, and we'll discuss more tomorrow.